For Chapter 7, Part 4. And we're going to start talking a little bit about periodic trends and how we ended up with the periodic table the way we have it today, as well as some general trends and um, kind of um, hints and tricks that we can use when we look at the periodic table to get a lot more information out of it. So here is a kind of rough breakdown of when we started identifying these different elements um, and kind of putting them in their place within our more modern understanding of the periodic table. So how do we organize 118 different elements in a meaningful way that allows us to make predictions and allows us to maybe understand we haven't discovered an element or something might be missing in between? So a lot of it comes down to patterns, and when we look at it, we recognize that Dmitry Mendeleev was the first one to kind of arrange these things in terms of their mass, and that we start seeing kind of a reoccurrence of different properties. So if you arrange the elements in terms of their mass, like we have here, and then you color coded them based on certain properties that they have, we kind of see this reoccurring pattern occur. And what we can do is, if we line those all up in a way like this, we start seeing something that resembles the modern periodic table. What this allows us to do is look at things and start seeing maybe there's some places where we have some gaps in our elements. Maybe another element will be coming, we'll be able to discover another element here. This type of periodic table that became the modern periodic table is based off of scientific law, and it's just based off of observations. It does not have any theory as to why these observations occur. Okay, so it's just a law, it's just observational based. All of these red ones explode in water. uh, these are all gases, things like that. It's not why do these all explode in water, it's just that they do. We're going to look at three different periodic properties: atomic size, ionization energy, and electron affinity. So, again, here's our modern periodic table. You're probably used to seeing these two guys down here, but this is actually the full expanded version of it. It just so happens that when we move the lanthanides and actinides down here, it fits much better on pieces of paper. We can fit more information on it, a little more resolution to it. So that's why you probably haven't seen too many expanded periodic tables before. We arrange them and talk about them in two ways. We have the periods, which go across, and the groups or families, depending on which source you're using. Some people call them groups, some people call them families. I like to call them families simply to help remind me that family goes up and down, and when we look on a periodic table, things that go up and down in the columns, they share similar traits, just like you share similar traits with your family members. But I guess you could say the same thing about a group, like, a group of people that all like, the same movie or whatever. So, when we have a periodic table, we know that a majority of the periodic table is going to be the metals. Very little of it is nonmetals. We have some metalloids, which have properties of both metals and nonmetals. And that we arrange the periodic table in increasing atomic number, right? So 1, 2, 3, 4, 5, 6, 7, so on and so forth. We read it left to right and top to bottom. The first periodic trend that we're going to discuss is ionization energy. And this is the energy required to remove an electron from the gaseous state of an ion or an atom. And so basically we can have multiple ionization energies because there are multiple electrons in most atoms. So the first ionization energy would be the energy required to remove the highest energy electron from the atom, so the one that's the furthest out. We're not going to pick the electron that's closest to the nucleus because that one's going to be very hard to take out. So we're going to take the ones that are on the outside first. The valence shell electrons, right? The ones that are on the outside. So the ionization energy, or the first ionization energy, would be the energy required to remove the outermost electron. The second ionization energy would be the energy required to remove the second most outer electron, third, fourth, fifth, so on and so forth. Realistically, we don't really go past like 3 or 4. But potentially, theoretically, you could. As we go across the period from left to right, ionization energy increases. Think about it. Electrons are added to the same principal quantum level, do not completely shield the increasing nuclear charge caused by the protons. So, as we go from left to right, we're adding more electrons. Ionization energy is going to increase as well. As we go down the periodic table, the ionization energy will decrease. Think about it. As we go down, we're going from n equals 1 to n equals 2, n equals 3, n equals 4, so on and so forth. That means by the time we get down to the fifth row, the fifth period, that electron, that's the outermost electron, is going to be really far away from the nucleus. So it's not going to take a whole lot of energy for us to rip it off. So it's going to decrease. So ionization energy, right, as we said, will increase as we go from left to right and decrease as we go from top to bottom. Electron affinity is another periodic trend that we're going to look at, and this is the energy associated with the addition of an electron. So this would be forming an anion, right? So electron ionization energy is the loss of an electron or the formation of a cation. Electron affinity is the formation of an anion or the addition of an electron. So it would be which elements want more electrons. And when we think about it, why would an element want more electrons? It wants to reach noble gas configuration. So as we go across a period from left to right, electron affinity becomes more negative or becomes greater. We talk in terms of negativities for electron affinities. The more negative the energy, the greater quantity of energy released, right? It really, really, really wants that electron. So it's going to release a lot of energy, become very relaxed when it gains that next electron. Depending on the atomic number, right, it will change a little bit, but again, as we said, as we go from left to right, in general, we're going to say that electron affinity will increase. And as we go down a group, electrons added are increasing the distance, so it's relatively small as well. The last periodic trend we're going to discuss are atomic radii, or the size, right? So again, when we talk about an atom, we're talking in general a sphere is what we're treating it as. So the radius would be a measurement of the size of the atom. The easy one to first talk about is the radius will increase as we go down a group. Think about it. We're going n equals 1, n equals 2, 3, 4, 5, 6, so on and so forth. So we're adding more and more layers, so the atom's going to get bigger and bigger. So as we go down the periodic table, atomic radii increase. As we go from left to right across the periodic table, you may be tempted to go, oh, I'm adding more electrons, so it should increase again. That is not true. It's actually counterintuitive. What's ending up happening is as we go across the periodic table, we're adding more electrons, but we're also adding more protons, which means instead of having one positive charge and one negative charge, we have 7 positive charges and 7 negative charges, and they're going to hold on to each other much more tightly and pull everyone together much closer. So in fact, as we go from left to right across the periodic table, we actually decrease in radius size. In addition to atomic radii, we can also talk about ionic radii, or the size of an ion, whether it's a cation or an anion, compared to its parent, the neutral atom. So what we have here is kind of a graph to kind of help with that. Cations will be smaller than their parent atom, which should make sense because we lost an electron, and anions will be bigger than their parent. So here the cations are in pink and the parent atom was in gray, and over here the parent atom is in gray and the anion is in blue. The only other thing we need to talk about when we're talking about ionic radii are isoelectronic series, or the idea that we could look at a trend in different elements and ions. And if they're isoelectronic, we're talking about them all having the same number. So an oxygen anion with a -2 charge, a fluorine anion with a -1 charge, a sodium cation with a plus charge, a magnesium cation with a +2 charge, and an aluminum 3+ cation. All of these have the same number of electrons in them, and we can look at their size in terms of that isoelectronic series. So this is just the last slide in our set, and is a summary of the 3 trends that we're looking at in terms of ionization energy, atomic size, and electron affinity. Now again, electron affinity, there's a lot of exceptions to the rule with this, but we want you to kind of just focus on the general trend with that. At this point, you should be able to complete all of your homeworks, as well as all of the resource materials that are provided to you. I strongly encourage you to go watch the resource videos and do the worksheets that are provided. They're a great resource for you. You can always email me or come to office hours for questions, so that we can discuss any of the issues you may be having. As I said, chapter 7 is a doozy. It's got a lot of material in it and will take some time to kind of internalize and work through. So I encourage you, if you have not started to read the text, to start doing that. Our test is coming up. Our second exam is coming up, in chapter 7 will definitely take a good portion of that, since there's so much material here. So I hope to get some good questions from everyone, and hope to see some of you in office hours.